Next, we want to show you another periodic interrupt called Timer2. Timer2 is a lot like SysTick. It has essentially two registers. One of them is a counter, and just like SysTick, it counts down, and another one is a reload value. In our particular case, it's called TAILR, and it's the reload value. Just like SysTick, when this counter goes from a 1 to a 0, it will set the trigger flag. This trigger flag is going to cause an interrupt to happen. Also, like SysTick, the value we put into the reload value will determine the rate at which it interrupts. Different than SysTick is this timer, and this reload value is now a full 32 bits wide. The code shown here on the page is the initialization code for this Timer2 periodic interrupt. We're going to pass in the value that we want to interrupt at. In our particular case, since we're running at 80 megahertz, the interrupt rate will be this value period times 12.5 nanoseconds, because that's the bus period. Like all modules, we have to turn on its clock, and so this is the clock bit for the Timer2 register. And after we turn on the clock, we will wait a while for the clock to stabilize. I have a couple of global variables that I'll use to debug with. This one will count the number of times the interrupt occurs, and this is a semaphore flag which gets set every interrupt. The 10 steps used to initialize the timer are now shown. We disable the timer during setup. We set it up as a periodic interrupt with a 32-bit counter. The value of period -1 is stored into the reload value. So again, the interrupt rate will be the value period times 12.5 nanoseconds. We set the resolution to run at the bus clock, which is going to be 12.5 nanoseconds. I like to clear the interrupt service flag in the ritual, that's step 6. We then arm that bit for interrupts. We set its priority by setting 3 bits of the priority 5 register. We enable, this is interrupt 23, and so we will enable interrupt 23 in the nested vectored interrupt controller, and then after the entire thing is initialized, we will then enable timer 2A. If the main program executes an interrupt enable, then interrupts at this period will occur periodically.
So we saw the initialization ritual for the interrupt service routine. So we now have interrupts happening on timer 2A. And when an interrupt occurs, the handler, which is the timer 2A handler, is called. And so we're going to look at what we have to do within this handler.
All right. So the main thread will enable interrupts. And then perform some task over and over. But when the timer goes from a 1 to a 0, it will set a bit in the timer raw interrupt status. This is the trigger flag which will cause the interrupt to occur. And so our handler then here will then be executed. Like most interrupts, we have to acknowledge that interrupt by clearing the trigger flag. The trigger flag happens to be in bit 0, and to clear the timer 2A timeout flag, we are going to write a 1 to the interrupt clear register. And when I write a 1 to bit 0, it will clear the raw interrupt status bit 0, which is our trigger flag, acknowledging the interrupt. And then these two steps are the body or the function, what we want to happen in the interrupt service routine. In this case, I'm just going to increment a counter as a debugging way to say, yes, this is running. And then we can use a semaphore flag to signal other threads that this interrupt occurs.
So for example, the main program could be checking this flag, and only when this flag is on, it could perform certain function. And when it's off, it's going to skip that function and keep checking this flag again and again.
Yes. So this is how a semaphore works. This semaphore flag here is set in the interrupt service routine. And then the main loop will look for that flag, and if the flag is set, then it will clear the flag, perform some function associated with the semaphore, and this whole process is repeated over and over again. So we have two threads, the foreground thread and the background thread, connected by a semaphore flag.